Okay, so let's talk about domain and range. Let's say we're given the function the f of x is equal to 2x plus 2. Okay, domain and range is very easy once you can visualize or graph a function. So let's graph this function. We're going to start at our y-intercept, basic slope-intercept form. We're going to go 2 slots up and 1 slot right. So we have 2 little points. And here we have our linear function. So the thing I want us to look at is, if I had to ask you, well, how far can this function go left and right? So if I had to talk about my x-axis, how far do you guys think it can go left and right? Well, most of you would say, well, it will never stop to the left and it will never stop to the right. Okay, so let's state that as a domain. Let's say our domain can go from negative infinity all the way to positive infinity, since it will never stop. Okay, well, what about our range then? How high can this function go? Up and down. How high can it go and how low can it go? Well, you might say again, it can go from negative infinity all the way to positive infinity. Well, you would be right. So let's see if we can make a conclusion on what our domain means. Well, our domain seems like it relates, it's right domain, it relates to my x coordinates. And my x coordinates is usually related to my input of a function. So now we can see, well, the input is related to the domain. The domain is related to my x coordinates, and my x coordinates is my input. So now we can conclude, well, my x-axis indicates my domain. Okay. Well, if my x-axis indicates the domain, my y-axis, which will be how tall my function is, indicates my range. And that's all. That's pretty much all you need to know. So let's go look at a different function. What if I tell you the f of x is equal to x squared? Let's graph this function. So this is a parabola. Okay. Another way we can state this is that it's quickly x is an element of all real numbers, which means that any real number can be placed into my function and I will get out every single value for my output. So my input can be all real numbers, and my output can also be all real numbers. All real numbers we can state with infinity. Okay, infinity just simply means it never ends. To be fair, we don't really know what infinity is because we can't really prove it, but we know it's never ending, or the concept, the idea of infinity, right? Just never ending. If you had to ask me to prove infinity, of course we cannot, because maybe with quantum computers, I'm not too sure about that one. Anyway, let's talk about this one. Well, if I had to ask you now, well, how far can this function go left and right? You would tell me the exact same thing. You would tell me, well, it can go an infinite amount to the left and an infinite amount to the right. So my domain, I can then state as it can go all the way from negative infinity to positive infinity. Well, what about my range? We can therefore again state that x is an element of all real numbers. This simply just means that this is a set. It's part of a set, you know. X is part of the set real numbers. Because it can stretch forever to this side and it can stretch forever to that side, left and right. But now, all of a sudden, when we look at our y-axis, what do we notice? Well, look how tall my function is. Well, it stops at this point. If it stops at that point, well, now all of a sudden we have a limitation of what my range could be. So the lowest point of my range is going to include 0. Okay, 0 is my lowest point. And from 0, we're going to use this bracket, a square bracket, for values, where there's some closed interval or some limitation. You'll learn more about this if I make an inequality or a video about inequalities where we have these type of functions. Okay, but for now, let's just get the idea about domain in range, what it means, before we get into the theoretical side. And I can go all the way up until infinity. Infinity, we have a parentheses or a bracket. This one would be a square bracket, because I can go on forever and forever, but I have a limitation at this point. Okay, you're starting to get the idea? I hope so. But if you don't, let's do one more. Let's say, well, the f of x, let's do two more actually, is equal to the square root of x. The square root of x looks something like this, starting at 0, and it goes all the way to the right hand side. This is what this function looks like, the square root of x. Well, now again, all of a sudden we can see, well, my function starts at 0 and it goes all the way to the right. So let's state that. Let's state what's happening. Let's state what the domain is. Well, the domain, I can see it ends at 0. We're going to say my domain is all the way from 0 to, where will it stop on the right hand side? It will never stop. So we have infinity. We can also say, well, x has to be greater than or equal to 0. So we can state the domain in two separate ways. I mean, there's more, but for now, let's just get this idea. And now we can see, well, for my range, however, I never go below the x-axis. I never go below this axis, but I can continue rising. Okay? So what would the range then be? Well, the range is also going to be 0 all the way to positive infinity. Because my inputs increase, so does my outputs. So both of these functions go up and right. It does not go down and it does not go left. If it does not go left, we stop at 0. If it does not go down, we stop at 0. Okay, but what if we do this? What if we now say, well, the f of x is equal to the square root of x minus 4. How does this function look? Well, now all of a sudden we have some sort of limitation again. Can we express this mathematically? Well, first things first, we cannot have a negative value inside of a square root. Okay? If I have this, this gives me a complex number I, which is a totally different subject or topic. When you get to complex numbers and three-dimensional planes, and you're working with z coordinates or I and r coordinates, imaginary and real. But maybe I can give a quick little explanation. So this would be all your real numbers, and you can find your imaginary numbers on this line. So let's say I had to ask you where's the value between 1 and 2, you tell me over here. Then if I ask you, well, where's -1? Well, -1 would be on here. So we can connect these 2 points. Anyway, that's something for a different topic. Now what happens here? Well, logically, I can see that through my previous explanation that if I have 4 minus 4, I can still get the square root of 0. So we know our limitation. Our limitation is going to be 4. So we're going to move to the right-hand side. So now I can state my domain as ending at 4 and going all the way to positive infinity. I can also say my domain, in this case, has to be greater than or equal to 4. Because if I don't do this, let's say I use 3. Let's say I use this point. The function does not exist at this point on a two-dimensional plane. So let's just say I use 3. I state that my domain is 3. Okay, so let's say 3 all the way to positive infinity. Well, let's see if this is possible. If I substitute into my function 3 equal to the square root of 3 minus 4, I get the square root of -1, which is I. And now, where do I find I? On my function, on my two-dimensional function with the x and a y axis. It's not there. So therefore, my domain would be incorrect again on a dimensional plane. Very important. X and Y coordinates. So this is the idea behind function and domains and ranges. My advice would be there's some functions you need to know. And if you know what the function looks like, it's very easy to state the domain and range. So for instance, if you see something like this, we know this is a linear function, so we know it moves up until infinity. Another example would be, let's say the f of x is equal to sine of x. If I had to graph this function, you might be asked, well, what's the domain and what's the range? Now, the domain and range will be very difficult to state if you are unfamiliar with how this function looks, right? Logically. That's why I always tell students it's very important to learn the names of things. That's why it becomes very easy to identify functions or identify certain things in mathematics. So this would be referred to as the amplitude. For those of you who are familiar with trigonometrical functions, we know that our amplitude goes from 1 to 0, 1 to -1, and so forth. And we continue going. The sine function can be stretched out an infinite amount of times. So this is what a basic sine function looks like, which would be my amplitude, which is this point, or from my x-axis to the highest point of my function. So I have an amplitude of 1. And now I can state, well, my domain of my sine function is, we have an infinite amount. We can go an infinite amount to the left and an infinite amount to the right. My range, however, is between -1 and 1. So this is how we can conclude certain ranges and certain domains. Otherwise, we can just mathematically calculate them, of course. For instance, in this case, where we have square root functions, we can obviously just assume that x cannot be a negative, or we can't have a square root inside. So in this situation, if we re-look at this one, the reason we said x needs to be greater than or equal to 4 is if I use some value lower than 4, this means, we have a negative value. Another thing we can do is we can set the left side equal to 0. And we can solve for x to find out where's my domain. So we can square both sides. The square cancels the square root. Anything to the power of 0 to the power of 2 is 0. So we have x minus 4 is equal to 0, and therefore x is equal to 4. So we can do it mathematically too. But by visualizing these functions, domain and ranges becomes literally a walk in the park. For the sine function, what we can also do is, again, like I said, there's multiple different ways we can express this. So if you want to be a little bit more advanced, we can also say, well, a domain includes all real numbers. We can write, well, this means that x is an element of all real numbers. We can also say, well, the range of sine can be written as -1 sine of 1. So there's many excuse me. There's many different ways we can express this mathematically. So get the idea, and we'll do some more practice questions.